The theme of my master's thesis is the study of the Haldane-Falicv-Kimball model's phase diagram. The aim is to understand the interplay between three very important areas in physics, being strongly correlated, disordered, and topological systems, and with that, studying new states of matter that may arise from their unification. Well, these may seem like three boring names, but they give rise to awesome phenomena. Before explaining why these areas are so important, one must first understand what is a phase of matter. We are familiar with the phases of matter that surround us: solids, liquids, and gases. In fact, the concept of phases is more general, and rigorously, we can say that two states of matter are in the same phase if with the manipulation of systems parameters like temperature or pressure, we can transform one into another continuously without abrupt modifications in their properties. With this definition, many other different phases can be enumerated, like metals, insulators, superconductors, and much more. Let's now head on to the three areas of interest, and start by strongly correlated systems. There are systems for which the interactions between electrons are very important. These systems are said to be strongly correlated. Let's take a simple example of an idealized system of this type with a bunch of atoms and half the number of electrons. If the temperature is high, the electrons have energy to move between atoms as they will, and different configurations are equally probable. But as you know, electrons experience repulsive interactions. So if we start reducing the temperature, their energy also reduces, and they start arranging themselves in such a way that they are furthest away from each other. And the configuration that satisfies it is one in which they occupy every other atom. Now you may notice that in this case they are arranged in an ordered way, and so they are in what is called as an ordered phase. This simple example represents a very important feature of correlations. They drive the appearance of ordered phases for temperatures below some critical value. The magnets that you find in your fridge or the promising superconductors are real examples of materials in an ordered phase. Our second topic of concern is disordered systems. Let's consider our system of atoms and electrons again, together with a dice. I throw the dice once for each atom. Imagine that I now suddenly gain the power of adding to each atom a charge proportional to the number that I get. Each atom will have a random charge, and therefore the electrons will experience a random potential from them. This randomness adds the so-called disorder to our system, of initially equal atoms. This is only an idealized simple example of disorder, but the interesting point is that there are some materials which are insulators due to disorder effects created by random potentials, and are different from insulators associated with correlation effects. Finally, let's look at our last area, topological systems. In our study, we are more interested in the so-called topological insulators. These are new odd types of materials which are insulators in bulk and conductors at the surface. The quantum states responsible for the conduction are topologically protected. What does this mean? Let's take a donut. If we deform this donut continuously, it can be molded into a mug, for instance. But we can never obtain a ball with a continuous deformation because it has no holes. The conducting states are protected by quantities which can be seen as the hole in our donut. A continuous deformation in the system won't destroy these states, and so they are robust against impurities and other material details. This, in connection with the fact that we have a conduction without dissipation, makes these materials very attractive and a hot topic of research. In my study, I will join two models together. The first is representative of a system with strong correlations which is intrinsically disordered, and is called the Falicov-Kimball model. The second is a very important model for a two-dimensional topological insulator created by one of the 2016 Nobel Prize winners, the Haldane model. The final product is the Haldane-Falicov-Kimball model. With the rising effort to find new topological materials, such combined approach ought to be taken in order to understand how topology can be stabilized and, more importantly, if new topological states of matter can be found.